So thanks everyone for the invitation. I'm very happy to be here. Lots of great people, great working environment. Looking forward to discussing with many of you. And so I've been asked to talk about what I'm doing, my field of research. Okay. Very good. Okay. And it's always a bit of a challenge for me to explain what I'm doing. So I have to think about it. It seems I'm doing many different things, but also not a lot. It's not clear. So the title is Combinatorics, Geometry, and Algorithms. So I'm interested in all those. What do I mean by that? What do I mean? Okay, I'll just use the keys. Okay. So combinatorics is the mathematical analysis of countable or most often finite collections of objects, combinations, permutations, orders, things like this. When this is given as, this type of data is given as input to an algorithm, we talk about discrete algorithms or combinatorial algorithms. By geometry, I mean Euclidean geometry, basic high school geometry, like points, lines, typically in low dimension. When this type of data is given as input to algorithms, and we study algorithms on this type of data, then probably what we're doing is computational geometry. And when we apply combinatorial techniques to finite collections of objects in some space, like maybe elementary objects like points and lines, then there's this field called discrete or combinatorial geometry. So I'm interested in the intersections of all these domains. And for the purpose of illustrating these interactions, I will start with a simple question on encoding, the problem of encoding point sets in the plane. Okay, so we'll look at points in the plane and then try to find some kind of discrete encoding. What can we say about this? It will be connected to matroid theory on one hand and complexity theory on the other hand. So I'll try to explore these connections starting from a very basic question of encoding points in the plane. So here's an example of a set of points in the plane. Okay, blue dots, plane. Okay, nothing fancy about this. This could be some kind, represent some kind of data. This could be experiments. This could be anything. Just define as a point set. There's a natural object that we can define on top of this, which is called a convex hull. This is an example of the illustration of the convex hull of this specific point set. There are many equivalent definitions of a convex hull. It can be defined as the sort of smallest polygon that contains all the points of the set. It can be defined as the set of all possible convex combinations of the points from the set, and so on. It's a very classical, super standard problem in computational geometry of giving a description of this convex hull. So you're given, for instance, as input the coordinates of the point, and you want to find a description of the convex hull, so the set of extreme points, those that are on the boundary of this polygon, and their order along this boundary. Okay, this is page 3 of one of the standard textbooks in computational geometry, where you have those definitions of a convex hull and then a number of fundamental algorithms for computing them. This is sort of one of the foundational problems studied since the 70s in the field of computational geometry. One definition that will be sort of helpful here for introducing the objects that I want to have a look at is this one. The edges of the convex hull are all the pairs AB, if you define them in clockwise order, such that for every other point C, the point C is on the right of the vector AB, right? So for any other point C, so if you take this vector AB, the triple ABC makes a clockwise turn. You agree with this? And the convex hull can be described as a sequence of such vectors for which this is true, and that form a cycle. Okay, if we have this, then somehow we found the convex hull. So this notion of a triple making a right turn or a left turn can be formalized. So we can define this. Actually, in order to find the convex hull, all we need to know about this set of points is not the actual coordinates, but it's sufficient to know that for every triple, whether for every triple, it makes a right turn, a left turn, or is collinear. Do you agree with this? If we have this information for all triples of points from the set, then we can compute the convex hull, right? So we can sort of discretize or summarize the information contained in the coordinates of those points into those triple orientations, and we have enough data to know, in particular, among other things, among other objects, it's not only for this one, but in particular for this object, the convex hull, it's sufficient to have this information at hand. It's easy to compute if you know the coordinates. This is really computing a 3x3 determinant, okay? And it encodes collinearities and so on. So we take the convention that if ABC makes a clockwise turn, then we assign a +1, a positive sign to this triple, and negative sign if it makes a counterclockwise turn, and 0 if it's collinear. Okay, so this is an encoding. And we have n³ such orientations. Now, not any assignment of signs to triples is representative of a point set, right? So in order for these triple orientations to represent a point set, there are some necessary conditions, right? They have to satisfy some axioms. Okay, we'll see later why we call them axioms, but some properties, right? I will not write all of them here. It's going to be a bit tedious, but I'll give an example of one. Is that if you have 4 points, and you should imagine that they look like this, but you don't need to know this, say PTQR, and if you know that PQT, TQR, and PTR are making clockwise turns, then it must be the case that PQR also makes a clockwise turn, okay? You can stare at the picture and sort of convince yourself that this should hold. This is only one of several properties that these triple orientations must satisfy. And these are necessary conditions, and we can list some necessary conditions that make sense, that are illustrated, and you can have sort of a geometric proof of them, right? You can like study the possible location of the points such that those are satisfied, and then prove that geometrically it must also satisfy the conclusion on the right. Okay? Yes? So this is basically saying that the point T is inside the triangle PQR. All right. So these things and these objects and these axioms have actually been rediscovered a number of times, or discovered by several people, or studied in different contexts. Among the first that I found, I'm not sure it's the first one, there's two people in theoretical chemistry who defined what is known as chirotopes. Okay? They were studying configurations of molecules, and this sort of orientation of, actually this was in free space, and the way that the atoms are located and their orientation, the orientation of the tetrahedra that you can find in the molecule, is important in chemistry for how the molecules function, and they define this as a theoretical geometric object. This has been pursued by Goodman and Pollack in the mid-80s roughly, and they would call them order types, okay? And so the order type of a point set would be this signature of triple orientations. And Knuth in the early 90s wrote a book. I'm not sure you can read the title from here. It's Axioms and Hulls. Okay. I believe the story was that Leo Gibas, a famous computational geometer, had an office next to Knuth, and Gibas was explaining to Knuth the convex Hull algorithms, and then Knuth had this idea of axiomatizing the properties of a point set so that we could compute convex hulls and also Delaunay triangulations and other objects that are derived from convex hull in higher dimension. And he wrote this thing, and sort of halfway through the book, he realized that it's been studied in other places, and he described connections to other objects. And Knuth defined his own set of axioms that are slightly different from others defined elsewhere, but equivalent. So very interesting literature on the early definitions of these objects, triple orientations. This is actually related to matroid theory. So I announced this. I'm not going to delve into this, but I'm sort of going to name drop and say there are connections to these objects that are, I mean, matroid theory is maybe together with graph theory and a few other fields, one of the major combinatorial theory in the mathematical sense, like a set of basic definitions and an elaboration on these basic definitions. The idea of a matroid is that it's a combinatorial abstraction of the notion of linear independence. Okay, so if you're looking at a set of vectors, you can think of real vectors or a matrix, right? And you look at the column vectors of a matrix. Some subsets are linearly independent, right? Meaning that no vector is a linear combination of the others, right? But not all subsets. The maximal size of a subset of independent vectors is the rank. Say if the column vector is a matrix, this would be the rank of the matrix. And these independent subsets, the maximal ones are called bases, right? So the size of a basis is the rank. And you can define some axioms that these independent subsets must satisfy. And if you just keep the axiom, you realize that this applies to other systems of sets, not only of vectors in spaces. And among them, if you look at the non-collinear triples in a set of points, these form a matroid, right? And this is just a fine independence of two-dimensional points, right? So you think of a two-dimensional, fine space, and the non-collinear triples are the maximal independent sets, so they form a matroid. So what is the connection with what I just said? If instead of encoding +1, -1, 0, you just remember whether it's 0 or not, you get a matroid, okay? So the axioms that the triple orientations must satisfy, you can sort of project them onto axioms of a matroid, right? So what we did by encoding those triple orientations is encoding the matroid and some extra information on the orientation. Another famous example of matroid is the set of edges of a graph where the independent sets are just the sets that induce no cycle, right, that are acyclic, right? So this is, of course, very standard example of matroid, and it is because these form a matroid that the greedy algorithm is able to find minimum spanning trees, right, for instance. So this is connected to, very much connected to graph theory. So I didn't mention the previous example, as I said, if you just encode non-collinear triples, so if you just remember whether a triple is collinear or not, you have a matroid. And if you orient those triples, what you get is an oriented matroid, okay? So this, in higher dimension and in sort of much more generality, is actually a special case of what is known as an oriented matroid, right? So not only you remember what are the bases, but you have orientations for the bases of your set system, okay, independent set system. So this theory is, again, one of the big theory in combinatorial analysis. It's been pioneered by people like Günter Ziegler, Bernd Sturmfels, Las Vegas in France, and there's a famous red book on oriented matroid, which is sort of the Bible of oriented matroids, in which in particular they develop many so-called cryptomorphisms between oriented matroids. So different sets of axioms for defining the same sets of objects, the oriented matroid, but just it's not obvious that these definitions are all equivalent. And among one such definition of oriented matroids are the chirotopes, the orientation of bases, as we did for our point set. Okay, so this was just to say, this is very much connected to sort of a big subfield of combinatorics, oriented matroids. Okay, back to our point set. So this is the connection from going from geometry to combinatorics. And now what I'm going to do is to pose a problem and then sort of explore the complexity of this problem and the connection to complexity theory. So the algorithms part. Okay, so here's the problem. I'll let you read. So suppose I got a set of n objects, and for every triple, I assign to each triple a sign in 0, +1, -1. And I ask you, can you assign a point in the plane to each of the n objects such that the sign corresponds to the triple orientations in the point set? Okay? So from the combinatorial input, can you reconstruct the geometry? Can you go in the other direction? Right? So in the sense, this is an inverse problem. I mentioned that the triple orientations must satisfy axioms, and I said that these were necessary conditions. They're not sufficient conditions. It's not true that if you satisfy the axioms, then there's always a point set that realizes these orientations. This is not true. And the complexity of this problem is actually hiding something deep. So here's an example. I have 5 points, and I sort of drew this table in which you can find every triple in some order. Then if you change the order, you should change the sign accordingly, but this is sort of the complete table. I left some entries blank, which involves twice the same point, so I must have triple of 3 distinct points. And here are some signs that I want to assign to them. And I asked you, is their point set a set of 5 points such that they're oriented triple-wise, exactly like indicated in this table, okay? And so this is the problem. So I'm not asking you to solve this problem here, but in fact, the answer for this specific question is yes, and this is a set of points that realize those triple orientations. So you can check that, for instance, 5, 1, 2 is making, or yeah, 5, 2, 1 is making a right turn, and it should be, yeah, 2, 5, 1 is -1. Okay, so 2, 5, 1 is indeed a counterclockwise turn. You can check that 2, 4, 5 is collinear, and indeed 2, 4, 5 is supposed to be collinear here, right? Okay, the 0 there indicates collinearity. Okay, so you can check that this set of points realizes the triple orientation. But sometimes you have examples in which all the axioms are satisfied, it is an oriented matroid, it is a proper carotope, yet there's no way to recover, to construct a point set that realizes those triple orientations exactly. And so this is sort of a mystery. There's this notion in matroid theory, the closely related notion of the missing axiom for realizable matroids. This is directly related to this. And then, okay, people dug a bit deeper, and then something happened in the late 80s. So for explaining this, I need to define this. So stay with me. You agree that every point is identified by 2 real numbers, the coordinates of the point, right? We're in real space, the plane, so 2 coordinates. So a set of n points is a collection of n pairs of real numbers, right? So it can be mapped to a point in R to the 2n. It's really 2n numbers that define a point set. Yes? You agree with this? And now, if I fix a carotope, if I fix the triple orientation, I can look at all the space of all realizations of this carotope as a subset of R to the 2n. You agree with me? So every point in that set would be a realization as a point set of n points in the plane of the fixed carotope. This is called the realization space of the carotope. And the question of whether the carotope is realizable is the question of whether the realization space is empty or not, right? Is there at least one point that realizes this carotope, right? So now a point is in dimension 2n, okay? This is also related to moduli spaces in algebraic geometry. So in 1986, Nikolai Minov wrote a theorem, proved the theorem, essentially. I mean, the proof was a bit sketchy, but everybody was convinced that if you give me any semi-algebraic set in dimension D, right? So a set defined by equalities and inequalities involving polynomials in the variables, every such set is stably equivalent to the realization space of some carotope. And I wrote rank 3 because this is exactly what I define, like triple orientation of points in the plane, right? So that means that, what does it mean? What's the idea there? So first, what does it mean to be stably equivalent? I will not define it here, but it's like resembles very much, including having the same topology, but just maybe having more dimensions. And the realization space would be some kind of shadow of this that would preserve the topology and preserve many features. So what it says, essentially, is that the realization space of a carotope can be arbitrarily complicated. You can have as many holes in there, you can have a completely arbitrary topology in particular. So it totally doesn't need to be convex, for instance. So it's not the case that if you have 2 point set that realize a carotope, all the interpolated version, you cannot interpolate between those two and have realized the carotope at every step. This is not true, right? So they're actually far from having any kind of nice property. This is what it's saying. Realization space can be very wild. This is what it's saying. Hence, the realizability question is probably difficult. And that is what Peter Shor explicitly wrote shortly after he understood Minyoff's theorem, and he wrote a paper basically saying Minyoff's theorem explained to computer scientists, right? Fantastic paper where he said, okay, a consequence of Minyoff's theorem, the fact that realization spaces of carotope can be a mess, this implies in particular that deciding realizability is NP hard, right? Meaning probably intractable, probably no polynomial time algorithm, right? It's not known to be in NP though. So it could actually even be worse than NP hard. So, okay, the realizability question is difficult, computationally difficult. This is what it's saying, and it's a consequence of Minyoff's theorem. Actually, why am I saying it can be worse? Maybe you've heard of the satisfiability problem, which is sort of one of the standard NP-complete problem. And in particular, if you can solve realizability, then you can solve the satisfiability problem efficiently, right? So if you have polynomial time algorithm for the carotope realization problem, you also have a polynomial time algorithm for the satisfiability problem. But actually, you have more than that. So the statement is that if you give me any system of equalities and inequalities of polynomials in n variables with integer coefficients, then there exists a carotope, a system of triple orientations, that is realizable if and only if the system has a solution over the reals. Okay? So it is complete, the realization problem is complete for solving polynomial systems of polynomials, equalities and inequalities over the reals. And this sounds much more general and complex, in my opinion, than trying to find a point set that realizes some triple orientation. Yet, they are polynomial time equivalent. It's the same, morally, it's the same problem, right? So this is likely to be sort of harder than the satisfiability problem, than any NP-complete problem. So for instance, if I give you these equations, I want to find 3 real numbers such that these equalities and inequalities are satisfied. I can construct a carotope, a system of plus and minuses, like the table I showed before, such that this carotope is realizable if and only if this has a solution over the real numbers. Don't look at it too much, I just put random equalities and inequalities there. I have no clue about whether this is true. Okay, just make things concrete. So we gave, some people gave a name to this family of problems that are equivalent to systems of polynomial inequalities and equalities over the reals. And this is the class EXIST-R, or ETR, the computational class, the complexity class corresponding to the existential theory of the reals, which is the set of well-formed formulas, like true formulas, that look like this, like existential quantifiers over real numbers, and then a Boolean combination of polynomial inequalities and equalities. So there's this logic signature of this theory in the sense, and it's a theory in the sense of logic. So how is that possible? How does this work? How does Minyoff's theorem work? How is that possible to do this reduction? You give me any system and I can construct this carotope. How do you construct it? Actually, this goes back a long way to 19th century work from von Staudt, who axiomatized projective geometry. And he showed that you could actually, okay, a way to see this is that you can actually do additions and multiplications using alignments of points in the plane, right? So for instance, on the left, if you start with the blue points, you have a point encoding 0. The sort of, the number corresponding to the point is their location, their coordinate on the the axis at the bottom, the horizontal axis at the bottom with an arrow. And if you start with a point representing 0, x, and y, you can add points that satisfy some Carotope relation, such that you can add 3 points actually, so that the third point has coordinates exactly equal to the sum of x and y. So you can compute sums. And the same thing for multiplication. If you start with 4 points corresponding, so this is a picture on the right, with 4 points corresponding to 0, 1, x, and y, you can fix the orientation of a few more triples involving 3 more points, and one of them, you know, will represent the product x times y. And by combining those gadgets, you can perform addition and multiplication. This is all you need for polynomials, right? And then you can encode the equality constraint, the inequality constraint also in the sign of some triples there. So this is just a glance at the sort of basic gadgets that I use to do this reduction from any polynomial system to the Carotope realization problem. Any question there? Am I making sense? Yes? All right. So this somehow more recently gave rise to a new complexity class. People realized that this problem was actually representative of a whole lot of problems, many in computational geometry, but not only, that are polynomial time equivalent, and for which we don't have any efficient algorithm, not even any polynomial time recognizable certificate. So it's not even clear that it's in NP. So this is it. It's a well-defined complexity class, so there's a well-defined notion of completeness there. And this is, you know, standing there next to P, NP, P space, and so on. All these problems are polynomial time equivalent. So the relation between this and NP, so we all know about the famous P versus NP problem, the power of non-determinism in computer science, one of course, major question in theoretical computer science. One way of defining NP is that you have a way, when the answer to your problem is yes, you have a way to efficiently convince people that the answer is yes. Is this graph Hamiltonian? Is there a tour, like a traveling salesman tour of length less than something? I can convince you easily that the answer is yes by showing you the tour. And you can compute the length of the sum of the length of the edges and say, yes, you're right. This is a Hamilton cycle with length, no more than this. If for the satisfiability problem, I can quickly convince you that there is a satisfying assignment. I can just tell you, okay, X is true, Y is false, and so on, and then you can check that this is indeed satisfying the Boolean formula. But if I give you a set of points, and I tell you, this is realizing the Carotope, well, probably you can check that the triple orientations, you know, work, and indeed it realizes. So why isn't the problem in NP? It is because sometimes the coordinate of these points have to be exponential size, so require exponentially many bits. So sometimes there are Carotopes. This has been discovered actually even earlier than the complexity class. There are Carotopes that are realizable, but only with points with huge coordinates, doubly exponential coordinates, meaning some coordinates require exponentially many bits. And this is why the problem is not known to be in NP, because we haven't found a way of having polynomial size and polynomial time verifiable certificate for positive instances. So ETR is not known to be in NP, right? And we know it's NP hard, so it would be equal to NP. But people think it's actually worse, that being ETR complete is actually worse than being NP complete, right? It's harder. What is known, though, is that it's contained in P space. So these equations, inequalities, equalities of polynomials over the reals, this can be solved in polynomial space, right? But nobody knows of any sub-exponential time algorithm, okay? So it is standing there, this new complexity class between NP and P space, and this is essentially everything that is known. So what is currently being done, what has been done since the past, I don't know, maybe 15 years or so, more, yeah, few decades, is listing more and more problems that were shown to be complete for this class. So polynomial time equivalent to Carotope realization. And one of them is, for instance, if I give you a graph, and a graph, I mean collection of vertices and then edges connecting some pairs of those vertices, I ask you, can you draw a set of disks, one for each vertex, such that two vertices are adjacent in the graph if and only if the two corresponding disks intersect. This is called a disk intersection graph, and so the problem is about recognition of disk intersection graph, right? Is this graph that I give you in sort of combinatorial form, just a list of vertices and edges, can you realize it in this geometric description as the intersection graph of a set of unit disks in the plane, right? It's a very standard way of defining geometric graphs. It's used, for instance, in applications like wireless transmission, right? Think of vertices as antennas, and then information can be transmitted if the antennas are close enough to each other. So this is sort of a standard way of standard geometry graphs in computational geometry, and recognizing them, so knowing whether you can realize a graph as an intersection graph of this problem is, again, polynomial time equivalent to Carrot-Top realization and a system of polynomial inequalities. It is an ETR complete problem. Okay? This has been first found by McDiarmid and Müller in 2013. See, the dates are getting closer to present. Another problem in computational geometry, realizations of polytopes. So it's known that any three-connected planar graph is the skeleton of a three-dimensional polyhedron. From Stein, this is called Steinitz theorem. But as soon as you go to dimension 4, deciding whether a face lattice, a lattice is the face lattice of an actual four-dimensional polyhedron in four-dimensional space, this problem is ETR complete again. Okay, so again, polynomial time equivalent. So recognition of face lattices that are realizable geometrically in dimension just 4, not arbitrary dimension, just dimension 4 is already hard, right? This is the proof, is actually the topic of a whole book written by Richter Gebert in 1996. Fantastic book, if you're interested in polyhedron. Okay, and now another problem, another example of problem that is not in computational geometry, that is also ETR complete, is a problem from game theory. If you've heard a little game theory, you've probably heard about Nash equilibria, and Nash theorem says that in every biometrics game with, you know, a number of players and strategies, and then players play mixed strategies, and then you see what the outcome is whenever players play. There always exists a Nash equilibrium. But if you add some constraint, if you ask the question of whether there exists some Nash equilibria with additional constraints, then the problem of finding one, satisfying this constraint, this is not always the case that there exists one, and finding one becomes ETR complete again. So here's a specific example. If you have a three-player game in matrix form, does there exist a Nash equilibrium such that every strategy is played with priority at most 1/2? Right? Deciding this is ETR complete again. So there's a whole series, and this is quite recent also. It started in 2017 with Markus Schäfer and Stefan Kovic. They found the first instance, but there's a whole series of papers exploring ETR completeness in the field of game theory and finding Nash equilibria with added properties. So this opened up, you know, venues in other fields in computational game theory. So together with Markus Schäfer and Tilman Mitsov, we put online very recently a compendium, updated compendium of ETR complete problems, together with an introduction to these notions, examples, and so on. It is still being revised. It is an early draft. Hopefully it's going to be published in a Bolyai volume edited by Janos Pák. But it's online, and there's an introduction to this whole complexity class. Lots of updated list of lots of ETR complete problems and dozens of open problems, open questions related to the complexity of some problems and the relation to ETR. So the conclusion there is that there's a gap, you know, in having a computer understand the description of a set of points, right? There's the Euclidean geometry compared to combinatorial information. There's this gap there. Representing point set precisely somehow involves an added complexity that is really materialized in this complexity class in these examples of point sets with exponential coordinates and so on. So there's really a gap here in the combinatorial description, the combinatorial objects, and the actual geometric objects. And I like this quote from Don Knuth about what we can have computers understand. And this is the end of my talk. Thank you very much for your attention.
So you mentioned that the axioms that are known are incomplete, right? But is there some more information about that? I mean, is there an actual incompleteness theorem or something more that you can say about that?
I mean, the fact that it's computationally hard indicates that somehow there's no way to find additional axioms that would capture everything. If there were, or if they were at least not efficiently testable. So it is the materialization, in my opinion, of a strong obstacle there in pursuing. I mean, there are variants of these problems. I mean, there's a whole set of problems related to matroid realizability, but also not only real realizability, but realizability over other fields. And there's a lot of work there and lots of questions. And this is also related to the missing axiom question. But I think essentially this computational complexity result is an answer to this. It's sort of hopeless to try to extend. But you can define other things. You can add more information on top of it and sort of have even on point sets in the plane. You can have sort of higher rank matroids, oriented matroids that are defined that sort of capture more combinatorial information. But it's hopeless to have a complete set of axioms that you can efficiently test, at least, that captures this. You will have to resort to some, it will not work because of that. You know? But it's a deep, I mean, if you realize in other fields, in other spaces, then there's a whole set of other questions also related to things like Giancarlo Rota worked on matroid realizability, which is kind of different from what I said. But yeah, it's essentially hopeless.
Thanks for your talk. I have a technical question about the slide where you presented Neff's theorem about the stably equivalent stuff. Yes, so the thing that puzzled me here is the size of the two space. I mean, if you fix n, the number of rank 3 cherotop is bounded. It's bounded in terms of n. But if you don't fix the degree of your semi-algebraic set, the topology of the semi-algebraic set is arbitrary. It depends on the degree of the semi-algebraic set, but the two seems unrelated. So is there something I don't understand there, or it's hidden in the stably equivalent?
I think it's hidden in the stably equivalent definition. Yes, okay. Yes. I think you can have universality result even for bounded degree systems also. But I mean, you're definitely right that this is a concise statement of something that deserves, some care, right? But what is certain is that whatever the system is, the rank 3 cherotop is sufficient, right? But you can also restrict the type of system you have, and you keep universality there, right? So, but in fact, and actually the notion of stable equivalent, I mean, it's really difficult. And I showed Hector Gebert's book, and very recently people found a bug in the definition of stable equivalence in that book, right? So it's a subtle question. It includes projection, rational transformations. So there's a lot going on. But you're right, this is, this deserves details that I didn't want to show. Thanks, yes.
I just have a question about the reduction with the multiplication, for example. Here, so it seems that you use the fact that some lines are parallel.
Yes. So you have to have a line at infinity.
Okay,
so this is yes. So indeed, exactly. Yeah, this is something that I put under the rug. Definitely. So yes, you have two sets of, two parallel lines to the first one, right? And then you apply, I think in France it's called Thales theorem, right? And but then parallel means that they actually intersect at infinity. So there's a point on the line at infinity which they intersect. So you would have to do this in the plane. You would have to do a projective transformation which puts the line at infinity back in the plane. So there's a hidden line there. You're right. Yes, but otherwise it works. It's sort of easier to see in the projective version with one line at infinity. Yeah, thanks for noticing this. Good point. But you can do it. Well, thank you.